Well, welcome into my garage, and hope you and your family are all doing well, staying safe. So this week we're talking about Physics 2 lab, Faraday's law. What Faraday's law has to deal with is that when you have a magnetic flux, you have a magnetic field passing through a closed loop of wire. If you can change that magnetic flux by either increasing the magnetic field or decreasing the magnetic field strength, that change in magnetic flux is going to induce a current, and that current in turn is going to carry with it an EMF or a voltage. And so what we're looking at is by changing the rate at which the magnetic flux changes. So if we can change the magnetic flux faster or slower, that should have an impact on how much voltage we're able to induce. And so that's what this experiment all gets into. So let me get this all set up for you, and we'll talk about how it's going to work. Let's take a look at this setup. I got my LabQuest right here. Now I've got my LabQuest talking to my iPad over here, so you'll be able to see a little bit larger screen when we do start talking about these results over here. But LabQuest connected to an instrument amplifier, and what this thing does is, just because we're going to be talking about such small voltages, it's going to allow us to dial in and detect those tiny voltages that we are going to be inducing over here. All right, so that's connected over here just really to some wire. I wrapped some wire around this PVC pipe, just a hollow pipe right here. This particular one, I wrapped the wire around 25 times, and so we got the leads connected to each end of the wire. So we got 25 closed loops of wire. Now, in part two of this experiment, we're going to use this second PVC pipe. This one has 50 loops of wire connected around it. So we're going to see how does that impact the voltage when we have more total area because we have more total loops of wire. Over here on the end of my little stick, I got a magnet attached right here. It's a relatively strong magnet. Now these are fragile, so I'm going to be dropping this stick right here. We're going to drop this magnet through this PVC pipe. And the stick is there just so the magnet can't be rolling over as it's falling through the pipe. And this pad is here just to protect this fragile magnet that's not going to land on anything hard and cause it to break. So it's going to look something like this. This PVC pipe is going to be here at different angles. We're going to use some different angles so that at a shallower angle, the magnet's just going to kind of slide down through the pipe kind of slowly. We're going to gradually increase this angle so that as the angle becomes larger, the magnet's going to fall faster through the loops of wire. Alright, so here's what's basically happened. As this magnet passes down through this loop of wire, as it approaches here, this magnetic flux is now increasing because this magnetic field is getting closer and closer to the wires, so you're getting a stronger magnetic field and a larger magnetic flux. But then it's going to pass out the other side, and as it passes out and falls now down toward the bottom right here, now this magnetic flux is going to be decreasing because the magnetic field is getting farther and farther from the magnet. And that should give us some results kind of like you're seeing right here. I did just one little test just a few minutes ago, and you get this spike right here. You get 0 voltage. All of a sudden the magnet's approaching the wires. You get a spike. As it's descending away from the wires, you get a spike, but notice it's down here on the negative side, and then it goes right back to 0. And what we're going to be trying to do in this lab is finding a couple of things. Finding what is this peak value right here. If I can come over here and do it on the right screen, it would help. Okay, so if I can touch and get my little circle there up to the highest little point, and sometimes this is the most aggravating part, getting it where it needs to be, right there. Okay, so if you get the little circle up at the top of the peak, we're just looking for what was that peak voltage. So here, 26.2 millivolts. The other thing we're going to want to do is find the area that's underneath this curve. If you look at your data tables over here, if my screen adjusts real quick, we're going to test 4 different runs, so 4 different angles. For those 4 different angles, we're going to get the peak value that was produced. we're going to get the integral, which is a fancy way of saying we're looking for the area. What's the area under the curve as the magnet approaches the loops? What's the area under the curve as the magnet goes away from the loops? And then we're going to repeat that same process for using 50 coils of wire right here. So what I'm going to do is I'm going to take a few minutes. I'm going to run all this data, come back, show you the results here on the screen. So I tested our 25 coils at 4 different positions. Started here, kind of leaned over pretty far, worked my way up till I dropped it straight down on trial number 4. Right? And I ended up with these results right here. So you can see these are in order. Purple was trial number 1, green was number 2, blue was 3, and the red was number 4. So what we want to do is get now what's the peak value for each one of these trials. So you can see right now I've got a little circle up at the peak of the purple trial. So trial number 1. All right, so coming over here to my data table, peak value trial number 1, that was 11.7 millivolts is what that was measured in right there. Okay. So we need to do the same thing for these other ones. So I got to come back over here to the actual lab quest and try to get the peak here on this green one. All right, let me go ahead and do this one other way. Let me just go ahead here, take this graph. Let me just zoom in right here. So I got a little wider space to work with. Now, there we go. All right, so up at the top of the green peak, we're now at a peak voltage 19.3 millivolts. All right, while we're here, while we're already zoomed in, let me go ahead and zoom this in a little more. And if I work on the right screen, it'll help a whole lot. So let me zoom this in a little more. All right, so we're zoomed way in now on this green peak. And let's go ahead and talk about the second part here, finding these integrals. So what I want to do is I want to highlight out here from when this first started to increase and highlight right there until we reached kind of the midpoint. And now from that, now I want to go to Analyze, and now I want to go to, come back over here so you can see what I'm doing. Come to the Integral tab, and I'm looking at right now this green peak. All right, so let's come over here so you can see what we're looking at. All right, so you see that green highlighted area right here. We're finding the integral. And it tells us right over here, that integral is 0.46005. And so that's going to be the value of my approaching integral. That was the first half of the curve, 0.46005. Units on that, these would be millivolts times seconds, because calculating this area, you're doing the x-axis times a y-axis, so millivolts times Tesla is what you end up with. All right, we're going to do the same thing over here for this bottom, this negative integral. So let me come back to our screen here. Let me undo what I did on the first one. All right, so uncheck that green integral. And now let me highlight this negative side of this graph. And now go Analyze Integral again, still looking at the green one. Right? And so right now you can see, okay, we get a negative value, this time negative 0.47622. Camera adjust there again. All right. Now we need to go back, do the same thing for the purple. We need to do the same thing for number 3 and number 4. So all I'm going to do is I'm going to come back over here, zoom back out on my graph so that I can do that same analysis, go back to the purple and get the integral. And for number 3 and number 4, I need the peaks and the integral. So I'm going to pause recording while I do that, then I'm going to show you those numbers. Okay, so here we are with the results from part 1, using the 25 coils, again, using 4 different angles, so we're getting kind of 4 different speeds right here. Now this graph, again, this graph's going to be on canvas for you to see, and remember, these are in order from, number 1 at the purple all the way over to number 4 is the red. So some of your questions are going to ask you to compare these things right here, compare their shapes, compare their peak values, but also to compare these integrals again. So just look closely, at these numbers right here. All right, so what I need to do next is I'm going to repeat the same thing for using the 50 coils. Again, 4 different angles, so you get 4 different speeds. I'm going to post that graph on Canvas as well. So give me a minute, I'm going to run that experiment. I'm going to come back and look at those results. Alright, so we repeated that with the same idea, but now using 50 loops of wire. And our results, you can see, look pretty similar here just before we start ever analyzing any numbers. But again, these are in order from purple, number 1, greens 2, blues 3, reds number 4. You can see how these peaks are growing in size right there. So we want to come over here next. I'm going to get this data for you right here by analyzing these peaks and these integrals the same way. Right, so analyzing those results on part 2 using the 50 coils. Right, one interesting thing you might notice here, if you go back, you look at part 1, on part 1, what we ended up with was having a positive peak first and then a negative peak. Notice here we've got a negative peak followed by the positive. So what happened here is it was just kind of luck of the draw. Whenever I made these connections over here coming from my instrument amplifier, I must have connected these kind of the opposite way I did on part 1. If I were to reverse these connections and do this part 2 all over again, then I would have got the positive peak first, followed by the negative peak. Well, what these positive negatives all have to do with is really just the direction of the current. Which direction is the current flowing as the magnet approaches the loops? And then as the magnet goes away from the loops, that direction, that current is going to change. And so all that happened is part 1 using our 25 coils, and now in part 2 using our 50 coils, our initial current was in the opposite direction of each other. We could have accomplished that same change if I take my magnet right here, if I flip this magnet over, and right now I honestly don't know which side is facing down, whether it's north or south, but if you flip this magnet over, then that would also change the original direction of the current, and it would cause your spikes to reverse over here. All right, but I've taken each of them like I did on this number 4 right here, the red one, and went through, analyzed each one of those results here. So you get each of the peak values, you get each of the integrals as they approach, and each of the integrals as they recede. Now what I chose to do was just to go ahead and record the negative integrals as the receding value, just to be consistent with what we did up there on part 1, and chose to record the positive integrals as the approaching value. And again, had I switched my connections, you could have switched these 2 peaks anyway. So that really doesn't matter which one we're saying is approaching versus receding right there. All right, but those are all the results you need right there. Sorry about my handwriting up here. It's 19.9. All right, so I hope that kind of made a little bit of sense, hopefully. But if not, look, feel free, reach out to me. If you got questions, concerns, you're stuck on something, I'm here to help you. So let me help you if you need it. All right, y'all take care, and I will talk to you again soon.